Are we? All right. So it's really nice to have here Stefan Haller. He is based in Vienna. He's been with us for a couple of weeks. I think if you've been in the department, you may have seen him. He's doing really nice things about analysis and topology, distributions and manifolds, and he's gonna tell us some of this stuff. So thanks a lot, Stefan, and take it away.
Yeah, thank you for the nice introduction, and thank you for the invitation too. It's been a very pleasant and interesting stay in Utrecht, and I very much appreciate the opportunity to give a talk here in the seminar. I want to talk about analytic torsion, and my talk has 4 parts. I will start with a topological counterpart, like a so-called Reidemeister torsion. It's a topological invariant that had been introduced by Kurt Reidemeister in the 1930s. It was a topological invariant that was able to distinguish spaces which are homotopy equivalent but not homomorphic. So this is going to be the first part of the talk, the Reidemeister torsion. This is called the Reidemeister Franz torsion. There's a second name associated to that. Reidemeister introduced that for 3 manifolds, and that had immediately been generalized by Franz to higher dimensions. We'll see a few words about that and present it in a way that's suitable for the comparison with the analytic counterpart, which will make up most of this talk. So in the second part, I will try to explain an analytic approach to this kind of invariant due to Gray and Singer. What's an analytic counterpart? We start with a smooth manifold and we try to analytically capture something the Reidemeister torsion is. Then we'll have a break. At least this is my plan. This will cover the first hour. In the second hour, so this is still quite classical, that dates back to the 70s here. But recently, this Singer torsion had been generalized to contact manifolds, and sub-Riemannian metrics on contact manifolds. This is due to Haller and Stefan Haller for contact manifolds. We call that a little bit, and then what part? We'll move on to geometries on 5 manifolds. So 5 manifolds equivalent to a certain kind of geometry permit you to define similar torsion invariants for these geometries. We call that 2, 3, 5. Torsion, analytic torsion. For 2, 3, 5 geometries. And 5 manifolds. This would be given by a 2-plane field, which is kind of generic, and so this 2-plane field defines such a torsion. So this is the plan for my talk. We'll start with the Reidemeister torsion. We start with this finite CW complex. X, and a CW complex gives rise to a cellular complex that computes the cohomology or the homology. The cellular complex cohomology, and for what I'm doing, it is important to not just look at the regular cellular complex for the trivial system of coefficients, but we're going to twist this complex with a representation of the fundamental group. So in addition, we fix a representation of the fundamental group of this CW complex. We look at the representation of this fundamental group, it's a unitary group for simplicity. And we look at the cellular complex with coefficients in this representation. So the details of these constructions are not very important here, but basically you lift the CW decomposition to the universal covering. Then with the cellular complex on the universal covering, and it's now module over the group ring of the fundamental group, and you can tensorize using this representation to get a complex of finite dimensional vector spaces. So these are all going to be finite dimensional vector spaces after we twisted with this representation. The complex of finite dimensional vector spaces that computes the cohomology of X with coefficients in this representation. Here's the cohomology of X.
That's Q plus minus 1.
That is a Q plus 1. Thank you. I'm using cohomology because later on it's going to be ground complex and ground cohomology, so it's more natural. You don't get anything new into it's cohomology. And the idea, so differential here, we can call it DQ. DQ. The idea behind the randomized torsion is to cook out an invariant of the space X by looking at the determinants of the differential. The determinants of the differential in the complex and use them to produce an invariant. And in order to talk about determinants, well, here we have two different vector spaces, so it's hard to assign a determinant, but we can pick up metrics. And in particular, because we started with a unitary representation, these vector spaces here come with the emission inner product. So this complex finite dimensional vector spaces plus an emission metric. So we have an adjoint of this differential at our disposal, and we can look at the adjoint proposed to B. This is now an endomorphism on a fixed vector space, and we can look at determinant. Now, this endomorphism is often going to have a kernel, so this determinant is going to be 0. But when I write determinant throughout the talk, I always mean we only take the product of the non-vanishing eigenvalues. We skip all of the zeros we have here and just take the product of non-vanishing eigenvalues. And then what you do is you compute it, you look at these determinants in each degree, and you take an alternating product. So you take the product of an even cube, and you divide by the product of an odd cubes. And this is something like a graded determinant of the differentials in the complex. Here it's sort of taking the square. We don't want that. We want graded determinant of the original differential, so we take the square root of that. And this now is what you would call the graded determinant of these B square root. And this is essentially the randomized torsion. This is the absolute value of the randomized torsion. This is the randomized torsion is associated to this CW position X and the coefficients of X. It's absolute value. So this is the idea. And in order for this to make sense, I'm going to assume that the cohomology vanishes. Cohomology vanishes entirely. These coefficients. There are many situations where this happens. So I'm not giving you the full definition of the randomized torsions in the report. You can define that without a cyclicity assumption. You can define that for any representations, and you can actually make sense of the torsion, not just of its absolute value. But I'm just comparing that later to the Raysinger torsion, so this is kind of convenient. So the absolute value, so not the full strength of the invariant, but the essential piece for our purposes. So this is called the randomized torsion.
And Stefan, in this, I mean, because you're saying you're assuming the cohomology is 0 with these coefficients? Where are you using this in this definition?
Don't actually need that in this
Yeah.
definition. Okay. But it will not be the right thing to look at when there's cohomology.
Okay.
So basically, this is a positive real number we associate to a CW complex center in the representation. And there's a theorem due to Chapman. '74, and he proved that this invariant does not depend on the CW decomposition of the space X. Which is a different CW decomposition of the same space, you get the same invariant. It's quite a substantial statement here. It's a topological invariant. Portion. Not just the absolute value, but I'm putting it this way. It's a topological. It's rather easy to see that it is an invariant if under subdivision of the CW complex, but it's much harder to prove that it's actually only depends on the homeomorphism type. Okay, so that's the definition, and I would like to move on to a very basic example, namely the circle. What this gives for the circle is one. The circle has a very simple CW decomposition. You just need two cells, a 0 cell and a 1 cell. So this complex is going to be very simple. We need a representation, rho, a representation of the fundamental group of the circle. This is of course integers. We look at the representation, the unitary representation for simplicity, and actually with one-dimensional unitary representation. So we just have to tell what we assign to the integer 1, which representation is then essentially a real number, which I call E. Rho of 1, that be e to the 2 pi IA, and E is a real number. And then in this situation, the complex only has two spaces, has the 0 chains on S1, in these coefficients, and the 1 chains, S1, these coefficients. Both are just called the complex numbers as vector spaces. And then we have the differential here, just to be not. And if the coefficients were trivial, then we to this 1 cell we would associate the difference of the two boundary points, which would be 0, but now the representation rho sees that, and the formula we get for the differential is e to the pi a minus e to the minus pi a. If the representation here has sort of monodromy e to the pi a, so running around the full circle, you get this contribution, and here split it up such that running around half the circle gives you half the contribution, and running around the other contribution. So this is, you can rewrite that if you want to as 2i sine. So if we look at the torsion, we have to take d star of this operator, but this is just one complex number. This is simple, so we just get the absolute value. In this case, the absolute value of the torsion is just 2 times the absolute value of sine. Yeah. So this is a formula I would ask you to keep in mind. We will come back to that later when we discuss the analytic approach, where Ray and Singer consider the circle 2 and get the same result.
For instance, here you kind of forced acyclicity by choosing A non-integers.
Thank you. So this is the point I wanted to make actually. You see that this vanishes here, the differential vanishes even only base an integer. So then if this is an integer, then you get this is the usual cohomology of the circle. This is a copy of C in degree 0, the copy of C in degree 1. And if you assume it's a cyclic, then you assume it's not an integer, and then it makes sense. Okay. That's the circle. And then I would like to show you another computation that was the result of this computation that had been done by Reidemeister. He looked at length spaces. These are three-dimensional manifolds. You can find mentioning a group action. Proportioning is the free sphere by a group action. And he was able to compute the torsion of the space. Example. These spaces. Due to Reidemeister. And that is from 1935. Yeah. So you fix integers P, Q1, and Q2. You assume that P is at least 2, and you assume that the numbers Qi are co-prime to P. And then you introduce the length space L, or LP, Q1, Q2. It's a quotient of the free sphere by a certain action of the group residues not P. So we think of the free sphere as a sitting in complex two-dimensional space. So this is the space of all C W, complex number, such that this is more than the original. It's our free sphere. And this group here, residues mod P, acts on this free sphere in a manner that's specified by these numbers Q1 and Q2. So you acts on the couple C and W by definition. When you multiply the first variable AQ1 over P, is that, and in the second variable, we use Q2. So you act in the first variable, in the set variable with speed Q1, and in the second variable, W variable, we act with speed Q2. And observe that if you add a multiple of P to K, this is just the identity. Because then the exponent is integral. So this is an action, actually a free action of the residues mod P is equal by CP, so it's just C mod P times C on this free sphere, basically. The section is free because this is actually we don't get any fixed points in this case. So it's a free action on S3. So the quotient here is a nice smooth manifold. It's a free manifold, and the universal covering is S3. These are called length spaces. In this case, the fundamental group, of course, is this is like the group CP. Of course, we need a universal covering here. It's pretty clear, and we need a representation. So you complete the torsion, representation draw. And here you have some choices. We let K act by e to the power 2 pi r K, and then some integer on L is a multiple of P, and this is the true representation. We don't want that because we want it to be acyclic. So we assume that L P is not divided L. So this is our representation. And randomized computed the torsion of the length space with coefficients in this representation. So we computed the torsion of L. Stated only for the absolute value. And actually, I give you the inverse, and the formula is simpler. And what you get is 4 times the absolute value of pi L R1 over P times sine pi N R2 over T. So what is R1 and R2? These are the reciprocal residues of Q1 and Q2. So R1, Ri times Qi equals 1. So Q1 and Q2 determine also R1 and R2, and these are the ones that appear in this formula. So you see the torsion sees Q1 and Q2 because it sees R1 and R2. And you have this formula for each representation, so then we have this formula for each L. So the torsion sees something, but this numbers Q1 and Q2. While the fundamental group or the homotopy groups do not, they only see the P. And you can use that to classify length spaces. When you classify length spaces, you can ask many different questions. Like you could ask, let's say 2 length spaces, LP, Q1 and Q2, and another one, LP, Q1 prime, Q2 prime. And you could ask, are they isometric? I mean, this action by this group, this is by isometries. So the torsion space is a Riemannian manifold of constant positive curvature. You can ask if they are isometric. Or you could ask if they're differomorphic. This length space. You could also ask if they're homeomorphic. Or you could ask if they're homomorphic. And of course, we have trivial implications. If they are symmetric, then they're differomorphic. If they're differomorphic, they're homomorphic, and if they're homomorphic, they're multiple parallel. Of course, the second elementary part here is that for some numbers, there are some isometries you can write down. For instance, if I switch the numbers Q1 and Q2, there's an isometry which does exactly that. You have to switch the coordinates C1 and C and W. Or if you conjugate one of the variables, the W goes over to W bar, that means you replace Q with minus QI. So some of these length spaces are obviously isometric, and you can write down isometries if you have QI is plus or minus the number R QI prime mod P, where R is co-prime to P, and this is up to permutation of Q1 and Q2. In this case, there's an obvious isometry that will tell you that these two spaces are isometric. So plus and minus is complex conjugation in one variable. The R here you get if you use complex multiplication, both variables, and the permutation until you get by flipping C and W. So there, in these cases, these length spaces are obviously isometric. And what you gain from this computation was the torsion here. If you look at this equation you get here for all R, you are able to conclude that each length spaces are homomorphic, and this condition must be satisfied. This is what you get from using the computational torsion in this case. So that gives you a classification of the lens space up to isometry, to whichever you want. Well, with different methods, you can classify them up to homotopy equivalence with a different condition. The condition then is P1 times Q3 with R squared P1 prime P2 prime mod P. Up to sign, sorry, plus minus for integer R that's open. So that's exactly what we get if we multiply these two relations. There's definitely a weaker condition here than here. And you can explicitly find examples. Maybe I'll write it here. You look at the lens space 7, Q1, Q2. They're all homotopy equivalent. Just checking this criterion here. And the lens spaces 7, 1, 1. And 7, 1, 2. They're not homotopy. And this criterion here is not. So this is sort of what the brief story about the randomized torsion is.
How much does this depend on which representation I chose? I mean, I guess there are formulas that tell you, right?
Yeah, well, here the representation is in here. Correct. For the circle, the computation we had there was sine of pi a.
Yes.
And the a was the representation. Now, you know, it does. The dependence on the representation is the interesting part. And that's why we have to twist the representations. Also to be in the situation as asymmetric where everything is much less easy to explain. So
Yeah,
that's
so if I chose here, sorry, it's a good question. If I chose here to look an L which works sort of poorly with respect to Q1 and Q2, I wouldn't see it. Is that right?
I don't know by heart. There's something people use here. It's called Franz independent lemma, and he showed that if you use all L here, you can prove, but it's not entirely straightforward. It's just number theory. You can prove that this condition will be met, but it's not. It's not so immediate. Okay. Sure.
So I'm a little bit confused with this theorem of Stefan that we in the 75. So, this theorem said that if they are homomorphic, they have the same random torsion, right?
Yeah, you also have to like move the representation of the fundamental group with the homomorphism.
Sure, but then, so in this diagram, you say that if they are homomorphic, then this condition should be satisfied. How don't you need to know that if they're homomorphic, they have the same random torsion? Or am I confused?
That's how you get it. If they're homomorphic, so you know that this expression must be the same. If you replace Q I with Q I prime, so that means replacing R I with R I prime, you must get the same thing for all L. And this is the torsion for one lens space, and then you have the prime torsion. They have the same torsion if they're homomorphic, so this expression that here must be the same.
But you need this theorem that if they're homomorphic, they have the same torsion.
Yeah, don't ask me how randomized.
Okay, this is what I was not sure, because you say that this is randomized, but then
I cannot say how he resolved that in his paper. But there's something in between here. That's the concept of a simple homotopy equivalence.
okay, I see. No, just to understand that I don't understand.
Yeah, that is a good point.
Okay.
I don't know if he like proved some independence of the CW decomposition. Okay, and then in the next part, I would like to move on to the Racine torsion, and the idea here is to replace this cellular complex or CW complex with the Dirac complex of a smooth manifold or Riemannian manifold. The second part where is the torsion. This is done in 1971, I think was the paper. We take a closed manifold, closed smooth manifold, and we look at the Dirac complex. 2 forms of A. Differential. It was 1 form of A. And so on. It's well known that the Dirac complex computes the homology thing. Again, we need to get this representation in there. In this picture, it's the easiest thing to do is to twist with the flat vector bundle. So we twist the Dirac complex with the flat vector bundle F. So F is a flat vector bundle over A. So that's just what it says. It is a vector bundle with a flat connection. In the flat connection, if you do parallel transport around closed loops, you will not get any holonomy because it's flat. I'm sorry, if you do parallel transport around contractible loops, you won't see any holonomy because of flatness. But if you do parallel transport around non-contractible loops, you may very well pick up some holonomy. The simplest example would be maybe a trivial bundle over the circle, trivial vector line bundle over the circle, and if you have a connection that's given by some constant ADT, if you just do parallel transport in a little neighborhood here, you'll stay in these leaves. But if you do parallel transport globally, the position might actually change. The holonomy around that loop that's not closed will be like the linear map given by multiplication with this number. Or another example you might have in mind is the Milne strip. Consider this is a vector bundle over the circle. If you go around once, you will flip this line, this fiber, this is multiplication by -1. So these flat vector bundles are intimately related to representations of the fundamental differentiation. It's just easier in the Dirac complex to work with the flat vector bundle. So we twist the Dirac complex with this flat vector bundle. And it computes Dirac cohomology. And we would like to complex. We would imitate the construction of Reidemeister. We would like to define a weighted determinant of this Dirac differentials. So that's before we pick up, we consider adjoints of this Dirac differential. In order to get adjoints, we need a Riemannian metric. G on F, and we need, for the vector bundle, we need a fiberwise summation metric on F. And these geometric choices provide adjoints, formal adjoints of the Dirac differential. And then we can, it's very natural to look at the Hodge Laplace type operators. you get by the E, Q, and so on. Rothschild Laplace operators. And the determinant or distortion we had before, at least on the formal level, so we had we wanted the greater determinant of E star D, whatever it means. Yeah, but formally, this is what we would like to consider. And you can rewrite that in a simple way using these Laplace type operators. And you can rewrite that as product of the determinants delta Q minus 1 to the power Q times Q. This is a very simple formal computation. The point is the determinant of this Laplacian here is the determinant of this operator plus the determinant times the determinant of this operator. If either wasn't well defined, but in the finite dimensional complex is definitely rigorous. And also, if you change the order here, the determinant will not change because this operator the other way around, they are going to have the same non-trivial spectrum. So this is a formal computation that allows you to rewrite that what we would like to have in terms of these Laplace type of operators. And analytically, these Laplace type operators are nicer than these operators because these are going to have an infinite dimensional kernel. They're not going to be elliptic operators, but these are very nice operators. These are elliptic operators, and all is known about that. So you can write it in this way. Note that it's not an alternating product, but the Q is entering here.
And again, here you quotient out the kernels.
Yes, again, these determinants are written down are always. I mean, we don't know yet what it should be. I will make it more precise, but it's always going to be the product of non-trivial eigenvalues. Just disregard the zero eigenspace. In this case, actually, it's equivalent to the cyclicity assumption. Say cyclic and the functions are invertible, do not have zero eigenspace. There's a Hodgkin composition. Okay, so we need to make sense of that. What is the determinant of the Laplace? So this is an elliptic operator in a closed manifold. You know that the spectrum will be isolated eigenvalues of finite multiplicity, and they will tend to infinity at a rate that depends on the dimension. But certainly the product of these eigenvalues will diverge by all means. Yet there's a very elegant way of assigning finite values to these determinants using zeta regularization. And that's what I would like to explain a little bit now. And we'll start with an example. So suppose we would like to compute the product over all positive integers. So this is the third one times 2 times 3 times 4 times 6. And so what should that be? This the sequence of numbers kind of looks like the spectrum of the Laplace surface. Same rate of divergence. What should that be? The idea when it comes to zeta regularization is to look at the zeta function that's associated to the sequence of numbers we have. And the zeta function is just the sum. You take these numbers, in this case, just ordinary integers, and you raise them to the power minus s as a complex variable, and you sum over all of them. And for this particular sequence, and this very familiar zeta function, this is just a Riemann zeta function here. That will converge as soon as the real power of S is larger than 1 for very elementary reasons. And the idea is to differentiate that, the derivative of the theta function. If you differentiate that, you get the logarithm of n here, and then you minus 1. So this is rigorous as soon as the real part of S is larger than 1. But if you now formally put S to 0 here, then this term disappears. You get the sum over the logarithms, which is the logarithm of the product. So the derivative at 0 should be the logarithm of the product of numbers. So formally, the derivative at 0 is minus sum of the logarithms. So that's minus the logarithm of the product we're interested in. So if we want to assign a value, we would be led to assigning the value e to the power negative of the derivative of the theta function 0. Well, and this theta function is very well studied. In particular, you know, the theta function that extends meromorphically to all of the complex plane. There's a single simple pole at s equals 1. And classically, it had been worked out what the value of the theta function at 0 is. This was minus 1/2. And it also been worked out what the derivative of the theta function at 0 is. And it turns out to be minus log relative power. So the plot that in here, the product of all integers is the square root of the power. And that's the idea behind theta regularization. This is a very intriguing way of assigning finite values to these converging products. And you can actually do the same thing with the spectrum of the Laplace operator, with the spectrum of elliptic differential operators. Large generality. So we got to try to imitate that and try to see the function of our Laplacian. So we Q for now. What would that be? That should be some, we take the eigenvalues, the non-zero eigenvalues of this Laplacian, raise them to the power minus x and sum over all the eigenvalues we have. That's it. So the function is related to the spectrum of this Laplacian. You can rewrite if you want in terms of traits, complex power of this Laplacian. You can rewrite, and that's actually very helpful, using a Mannich transform. You can rewrite that this form. So this e minus. So here the complex power of the Laplacian is the complex powers of the eigenvalues, but you can rewrite that in terms of the exponential of the Laplacian. Here's the gamma function that appears, and this transformation is from Mannich transform, and there's really no big deal at this on the formula level. Just take the formula for the formula for the gamma function, Euler's formula for the gamma function. And then we substitute lambda t for t, and then we get formula this time. lambda T. You now imagine the lambda I here. And sum over all the i's, then the left hand side is gamma function times the zeta function we had before. And then the right hand side here you get the trace of the y exponential. It is actually exactly what Riemann did in this paper. So that works quite general. It's no big deal, and analytically it's very convenient to deal with the equation. And we got the required analytic properties of the heat operator to make this integral happen and get a rigorous definition of zeta function, extension, meromorphic extension, the value at 0. So that's the idea. And now there is a lot of analytic analysis that enters at this point. This operator e to the power minus TB, the zeta operator has a smooth kernel. X and y. So that is known. So this is a t is larger than 0, x and y and the manifold n. That's a smooth kernel. It's a smoothing operator, but it's also smooth in t. And as t approaches 0, this operator soda weakly converges to the identity, which of course is not a smoothing operator, it's very singular. But we do have an asymptotic extension for the heat kernel along the diagonal. It's a heat kernel on the diagonal that makes an asymptotic extension of the form some coefficients e to the power g minus n dimension over 2. 2 here is the order of the operator, it's a Laplace operator, second order elliptic operator. A asymptotic expansion like this, the heat kernel along the diagonal. So this is, one has to work here a little bit and use classic elliptic analysis to get that. So this is well known and in fact works in larger generality for pseudo-differential operators due to the result of sealing. Only that you might see more. In addition to these terms, you might see more terms. But that's well known and it's required to proceed. So this is as t goes to 0, of course. These terms that appear here, HA, these are local. So if you know your geometry and metric locally, you can work out these terms. And then, because we're dealing with differential operators, they vanish if G is odd. So things does not remain true for two differential operators, but differential operators have an additional symmetry that causes this vanishing here. And if you integrate over M, then we get an asymptotic extension. For the trace of the heat trace. And these coefficients here, these are not just real numbers, and these are just the integrals of the numbers A, G, X. To integrate that over. Integrate these local quantities over N, and you get numbers, and these are the numbers that appear in the asymptotic extension of the features.
Sorry, so the Laplace that you're looking at now, is that the Laplace 0, or are you still doing the Laplace Q?
Any Q, any fixed Q, or all Q at once, whichever.
Yeah.
Yeah, it's a little inconsistent. Maybe I should write the Q here all the time, but the notation gets not so there's a leading, so maybe I'll speed up a little bit here. There's a leading term, the most singular term in this expansion we have, the smallest power of t, most singular power of t is for j equals 0. That's the term A0 is the leading term. And this leading term gives you the y law, how fast the number of eigenvalues of this operator will grow. And this is the speed with which they grow is determined by n over 2. maybe I should write it out. So that's not the number of J, such that J eigenvalue is smaller than lambda. That's the total probably is like A naught. This is the leading term here. This expansion T to the power n over 2 and some gamma value gamma plus where is it? Say n over 2. That's not the leading term tells you how fast I'm going to slow down. And if you have this asymptotic expansion for the heat trace, this integral here becomes this integral here will converge as soon as the real part of this is larger than the 2. Because then n over 2 is the most singular value of t we have in this expansion as t goes to 0. We're going to assume a cyclicity, so this integral is always going to converge at infinity. But the problem is about convergence at t equals 0. And you can use this as a function extension, include partial integration here, and actually work out a meromorphic extension of the secant function to all complex plane. Meromorphic. Let's see. That's what we get from the sequence expansion. And it's going to be holomorphic, but where you know where the poles could possibly be. The poles could be integers of the form -2. And you can work about the residues. These are most simple poles. You can work on the residues. The residues are essentially the numbers we have here, the HA. But in addition, you have this gamma function here. 1 over gamma is an entire function. It has some zeros, and these zeros of the gamma function cancel some of these poles. And in particular, this zeta function is always going to be holomorphic at the zeta. Holomorphic. And the value at 0, sorry, using here, the value of the zeta function at 0 is just the constant term we have, So that we have very similar powers of t here, and many similar powers. Then at some point we hit the constant part. This is so this is A. For j equals n, we have constant. This is what's called the constant term, and this gives you precisely the value of this zeta function at 0. So we have the holomorphic function at 0. We can take the derivative there. Zeta prime at 0 makes sense, and we can define the determinant of the Laplacian using this derivative. So these aspects of the Riemann zeta function extend to Laplace operators. Actually works for elliptic separate positive operators and to the differential operators. Of course, you cannot expect a functional equation in this generality. But we can define the determinant of this Laplacian stuff. E to the minus zeta prime at 0. Something functional determinants. They're actually used in physics somehow. They have to regularize some products.
N was the
N is the dimension of the manifold. Okay. So we can now give a rigorous definition of this racing equation. This into account and actually then move on to an example. Consider the circle again. Try to compute that closer. the definition of Rainer Singer. Going to denote that by torsion, Ray, Singer, and it depends on the Riemannian manifold, the puzzle we twisted with, the Riemannian metric we had, and the fiberwise emission metric we had. And it's supposed to be, it's formally graded determinant of B star B. 1/2, and we have rewritten that as a product of determinants of this Laplace. And now comes what I put down here, the precise definition we take. The derivative of the theta function makes 0. And it's convenient to write the theta function in this term with the number operator in. So write it as a graded trace. For each q, we get a trace. We have some sort of alternating product after take the logarithm, this becomes an alternating sum. So the S here stands for graded trace, so we introduce a sign, -1 to the power q, and n is just q. On q forms. It's the q we have here. So that's the rigorous definition. That makes sense if you put all this analytic analysis in. Okay, let's move to an example. Let's do it for the simple. Again, we will take a representation of the fundamental group as we had before. Draw individual a real number. That's now integral. In this case, the cohomology of the circle with coefficients in the flat bundle you get from this representation. Manifest, and we have a torsion. And the sections of this flat bundle you have, they can be, of course, so the flat bundle we have here is just the associated bundle, the associated the universal covering. See, this is the flat bundle. And so the sections of the flat bundle then just become functions on the real line to the complex numbers that have some periodicity at the x plus 1 is rho at 1. This is a canonical way of writing the sections of this associated flat bundle. And here we have an orthonormal base e to the 2 pi I a plus a x okay, integral. So orthonormal basis to space of functions. Just Fourier series. If it was a trivial bundle, then you had Fourier series and no number 8. But now I think it's shifted by this number 8. And then so you can look what the spectrum of this Laplace operator had because these are actually undefined functions for the Laplace operator, and you get spectrum. It's just the Laplacian functions. It has spectrum 2 pi a plus a squared. Each of these is an eigenfunction, and this is the spectrum you get. So you look at the theta function, and you look at the trace, the power s, and this is not just the function functions. The function is 2 pi s. 2s. And that is again a classical theta function. that can be expressed using Hurwitz zeta functions to get 2 pi to minus z, just pull it out. And then if you just add over the positive integers, this is really the definition of the zeta, the Hurwitz zeta function at 2s associated to a, and then to sum over the negative k, you get another Hurwitz zeta function. 2s and then 1 minus a. Yeah. But the point is, in this very symmetrical case, we can get very classical zeta functions. In particular, the value of the zeta functions at 0 have been computed and the derivative at 0. So we know, so by definition, the Hurwitz zeta function is just because that's the definition of the Hurwitz zeta function that converges if the real part of s is larger than 1. And people have worked out the value at 0. It's 0. This is just 1/2 minus 8. People have worked out the derivative at 0. And then gamma function is up. This is the logarithm minus the logarithm of gamma a minus the logarithm of square root of pi. This is known as the Liach formula. So very classical, and if you plug it in, you get the Racine torsion of the circle. But with these coefficients, it's just again 2 times the sign. I was a little pressing on the brief here. Eventually you get the sign. How do you get the sign here? The derivative of this Hurwitz zeta function gives you gamma of a. Here you get gamma of 1 minus a. And there's Euler's product formula, gamma of a times gamma of 1 minus a that combines with you 1 over the sign. And this is how we end up with the sign here. So we get exactly the same formula we had for the right method torsion. Exactly the same formula. And this coincidence, this is no coincidence, it's a general fact. The Reidemeister torsion and the Racine torsion, they coincide. This is a result known as Shiga-Müller theorem. Independently by Shiga and Müller. There are 3 papers, 1977 to 79. And we show that the Racine torsion associated to the is exactly the absolute value of the Reidemeister torsion. So with this representation, as long as the representation is unitary. Yeah, the circle we verified that, but it's a general fact. The idea is the Reidemeister torsion here behaves very nicely with respect to gluing. And the true gluing results for the analytic torsion, and then comparison boils down to comparing standard tables. There is a more general result, more recent, it's smooth. And it tells you that the Racine torsions divided by the Reidemeister torsion of absolute value. This is an exponential of an integral over n, and here's some local factor. So in general, they're not equal. There are some, if the representation is not unitary, Actually, if it's not unimodular, and if this metric we have here is not parallel, then you actually get local quantities, and they don't agree totally. And it's this move has worked out. These quantities. The proof here pursuit is very conceptual and employs a very nice technique that's due to Witten. It's called Witten deformation. You pick up a Morse function and you deform the fiber-wise emission metric you have here using the Morse function. You replace this fiber-wise emission metric with e to the power the Morse function f times h. So, and put the parameter in here, h is h by e to the power minus 2 times h. And you know how the Riemannian torsion varies if you vary the metric by local quantities you can work out. But as t grows larger, the round complex will split into two parts. Part of the spectrum will converge to zero, many eigenvalues will converge to zero, and the remaining eigenvalues of the Laplacians will converge to infinity. That gives you a canonical decomposition of the round complex into a small complex and a large complex. And the small complex, in a very natural way, is isomorphic to the Morse complex associated with this Morse function here, just by integrating over unstable manifolds. So the small complex compares to the Morse complex. The Morse complex computes the randomized torsion, because it's more or less the CW decomposition. And then, of course, you have to deal with large part. But that's the basic idea. This is where you see how the analysis compared to the dynamics or to the combinatorics of the Morse function.
There's also this idea of Witten, how he moves at the Morse complex.
Exactly, yeah. He derives Morse inequalities using this approach. Because the small complex in the round complex that appears computes the cohomology and does the metonyms. Yes, that's his idea. So maybe one more remark here. The right-hand side does not depend on the metrics we picked up. That's sort of a corollary of the statement here, but the proofs are really the other way around. The first thing you do is you work out how does your torsion change, your analytic torsion change if you vary the metric. The Riemannian metric we have achieved, and then the fiber-wise emission metric. And it turns out that it varies by local quantities. And in the Riemannian case, we can really work out what these local quantities are. And what you see are like the Euler class, the Euler form. You see Chern-Simons forms. You see multi-Quinn forms, that is the top class. Very classical forms associated with the Riemannian metric in the method perhaps show up. And in the Riemannian situation, this can actually repeat. Okay, so this was the story about the Riemannian torsion, and now would be a good time for a break. And after the break, I'll try to tell you how this can be generalized to other geometries which are not Riemannian but sub-Riemannian.
Thanks a lot, Stefan. Maybe cut the recording for questions in case people. All right, should we start again? So yes, welcome again. I guess we just get to it. Yeah, Stefan, whenever you want to start.
Okay, so I will now move to certain kinds of sub-Riemannian geometries. The first one I would like to talk about is contact geometry. And in contact geometry, there has been an analytic approach to there has been an approach to the analytic. And this is due to Romain's contact manifolds. And that's from 2012 paper. The idea here, so we're considering closed contact manifold. So we have this hyperplane distribution in the tangent bundle, contact distribution. And we assume that the dimension is at least 3. And rather than 2n plus 1, at least 3. And the idea here is that there is a replacement for the Durand complex that really sees the contact geometry, and that's Homer's complex. I'm not going to give you the definition of the Homer complex, but I'm going to put formulas down in a minute. Just want to tell you qualitatively what it is. When you have a contact manifold, you can look at the contact plane bundle plus what the contact plane bundle. So this is what is called the associated graded bundle associated to the contact manifold. This is a vector bundle of Heisenberg algebras over it. So each fiber in is a Heisenberg algebra. So this is a V algebra of the form G1 plus G2. So G2 is one-dimensional and G1 is two-dimensional. And if you have bases, xi and yi in G1, and the brackets xi and y. So this is just what you can. And we can look at Homer's complex. And Homer's complex is a complex of differential operators. So you have sections of some vector bundle. And the vector bundle that appears here is the fiberwise cohomology of this Lie algebra. This is a bundle of Lie algebras over the manifold M. Each fiber is a Lie algebra. We fiberwise take the Lie algebra cohomology to get the new vector bundle over M. And this is the vector bundle that appears here in the complex. But really, it's not going to be important how this is done. I just want to mention that. Then we have a differential operator, the Homer differential. I'll take you to sections. The bundle you get that. Looking at the actual next to you. So then the point is there is a natural vector bundles associated to the contact manifold this fiberwise Lie algebra cohomologies. And the Homer complex is a complex of differential operators. So these are all differential operators. The Durand differentials all have order 1. The operators in the Homer complex might be higher order. And in fact, the operator in the middle dimension, this is Dn. We call the dimension is 2n plus 1. So in the sequence of operators, there's one in the middle, that's the Dn. And Dn will have order 2. Second order differential operator. And the other DQ with the other 1. But it's a sequence of differential operators, slightly higher order, and it computes the cohomology of M. And of course, I'm going to twist again. I'm going to twist with the vector bundle. So I'm going to twist the Homer complex with the vector bundle. And then it's going to compute cohomology with proficiency with vector bundle. Let's look at the formulas. I do not want to redo the construction of this complex. That would go different directions. But let's look at dimension 3. Dimension of n is 3. Then locally all contact manifolds look alike. These cohomology groups then the zeros cohomology, the algebra cohomology group is just it's just one-dimensional, and the second cohomology is two-dimensional. So that means that the complex then looks like functions on N. So this is sections. So sections in the rank 1 bundle, we take it to functions on N square. This is the operator. The zeros Riemann differential, then comes the first Riemann differential. And second Riemann differential. Then we're done. That is q equals 0, q equals 1, q equals 2, q equals 3. And here we have two components. It's just because the algebra cohomology is two-dimensional, and here we only have one component because the algebra cohomology is one-dimensional. And you can put down explicit formulas for this operator. This is just the series operator just differentiates in two directions, x1 and x2, and these directions x1 and x2 span the contact distribution. So the contact frame x1 and x2 span the contact distribution, and x3 is the bracket. And then the first operator that appears here is just differentiation, but only in the contact direction. And the round differential, the differentiating in the third direction too, we don't have it here. The second operator here, so this is the first order operator. The second operator is slightly more complicated. Second order, we differentiate the matrix of differential operators, so eats two functions and spits out two functions. So this matrix. So you see you differentiate twice here. Once in the contact direction, then again, once again in the contact direction. Here you differentiate in the transverse direction. So that's what their operator looks like, and the operator B2 then is very simple. It's just minus and so first order operator. So locally, that's what the Riemann differentials look like. And the point is, you can make sense of the globally, and it's intrinsic to the contact structure. It's totally canonical. No choices involved. To every contact manifold, you can associate this complex without making any further choices. It looks like that. So, and then one would like to play the same game. We would like to define analytic torsion associated to this complex. Slightly more complicated, but not much. We would fix the Riemannian metric, sub-Riemannian metric, and we fix the emission metric. On the twist width, and the sub-Riemannian metric on the contact plane field, and this is enough to provide formal H1s of these Riemann differentials. It's just because if you have sub-Riemannian metric in this contact manifold, that will give you the metric of this associated gradient here. And so you have fiberglass metric here, and then you use them to compute the H1s. So you get H1s, and you would like to look at the Hodge Laplace type operators again. But here is a little problem. So start with the operator delta n we will get in the middle part that would have en minus 1 star plus en star en. It's one of the operators we would like to consider, because if we proceed analogously to the racing case. But the problem here now is that the operator we have here, that's the one from the middle, this is fourth order operator, while this is the second order operator. So we do not expect very good behavior of this operator as I put it down here. And what Romain and we did is they just squared that here. And then we have two fourth order operators, and we combine these two. And it turns out that analytically this operator will behave just like an analytic operator. It's not going to be that.
What does sub-Riemannian indicate? What is a sub-Riemannian?
It's just a fiberwise Euclidean metric on the boundary beach.
So
this is sub-boundary respect to boundary running. You pick a fiberwise Euclidean metric. It induces zero in particular volume problem on the So you have similar problem with the operator delta in just one. The next one, this now has d and dn star plus d plus 1 star plus 1. We get this is fourth order, this is only second order, the square that we have two fourth order operators and they combine nicely. And in all other cases, all other Qs, we just take we have two second order operators, but we would like this to be fourth operator again, so that it has the same behavior as these two operators. So we spread them. And these operators are called the Haller. And to use these this is the so I put a C, we put a C for contact torsion, contact analytic torsion. It'll depend on your manifold M, on the contact plane field, on the boundary you twisted with, on the sub-Riemannian metric, and the fibrous emission metric. This is the data that entered. And what we want is something like it should be a graded determinant of B star D. So this is how we started out. Then you rewrite that just as we did in the Risinger kind of portion. We rewrite it in terms of these Rubers and Java operators. And it's almost as before. Alternating for actually this Q plus 1, maybe I skipped the plus 1 last time. So Q plus 1. The numbers here we had a Q the other time. Here now is slightly different. Numbers in Q will appear. And these numbers in Q, we need so Q is 0 going to equals Q if Q is smaller than Q is equal to if Q is larger than 1. These are the numbers in Q. In the Riemannian case, we have Q equals Q all the time, but now there is a jump in the middle. And that's just reflects the fact that the operators here. There's one operator that has a higher level. You have to account for that. When you do this rewriting, you rewrite this in these terms, just what you get. But also now these are fourth order operators for through and the Q. This is just a formal rewriting. And then as before, we would like to use the zeta functions associated to this operator here to make them rigorous. So we would like to define that by looking at the zeta function at 0. And it comes a greater trace. Again, this number operator in appears here. And here is Romain's and Java operators raised to the power s. this is what one would like to have as a definition. And then, of course, you have to make that rigorous. Make sure that this the powers here make sense for S. Real part of S sufficiently large. Make sure it can be extended meromorphically to the complex plane. And make sure it's holomorphic at 0, and define the determinants using intermediate 0. The analysis you need here is not elliptic analysis, but it's the Heisenberg calculus that helps you to make that precise. So the point here is that these Romain-Séchard operators, they are not elliptic, but when we consider them as in the Heisenberg calculus, they satisfy the so-called Rockland condition, which is the analog of the elliptic requirement to an invertible principal signal. The Rockland condition asks that the principal symbol in the Heisenberg sense is invertible in each representation. And these operators have the property. They have this Rockland property. This Rockland property guarantees that they have parametrics in this calculus. They can be inverted up to smoothing operators. And that's the key point. And they do have this property, and the Heisenberg operator guarantees you that you have parameters, and in particular, the heat operator, d by dt, that's this Romain-Séchard operator. It's going to have the parametrics. And from this, you get all what we had before. You get this heat operator as a smooth kernel, and the asymptotic expansion along the diagonal. You get again with local quantities. It has an asymptotic expansion which almost looks the same with minor modifications. Here now is a 4. That just reflects the fact that the operators we are considering now are fourth order operators. Before we had 2, the Hodgler partials were second order. And here I write D. This is not the dimension of the contact manifold, but this is the homogeneous dimension of the manifold. The homogeneous dimension of the contact manifold is 2 times n plus 1. That's even. So from this analytic point of view, a contact manifold feels like an even dimensional object. The asymptotic expansion you get here looks like the one from even dimensional. Yeah, you have the same features. You have these quantities that appear here can be locally computed, at least theoretically, but it's really hard to actually compute them. For odd J, they will vanish, but it doesn't give you anything because that D is even. So the vanishing of the odd J doesn't help us when you consider its value, or it's derived at 0. You get a Wiles law. It's the leading term here that gives you the speed of convergence, and the rate of growth of the eigenvalues is not the homogeneous dimension over the order of the operator. And the constant term is related to this. And once you have that, you can make sense of that rigorously. It's not guaranteed that this extends in more manner to 0. And you look at the derivative, have made sense of this distortion here. Yeah, you just replace the elliptic analysis with the Heisenberg calculus.
This structure, you want that very principle, you can take a higher of distribution model, making the operator higher, even higher.
So whatever fitted manifold you have Romain complex, provided that this diagonalized Lie algebra column, which is considered it's very weak assumption. So you can say large classes of input manifolds have Romain complexes.
Yes.
The analysis works fine in a graded sense. These are not going to be Rockland complexes in general, but they are going to be Rockland complexes in a graded sense. Hopefully, I will be able to say something about that at the end of the talk. These operators you would assign here, you wouldn't even consider these operators because of this additional grading properties. The point is, in general, this operator, this has an additional grading here, this space, and this has an additional grading. And the operator here poses it to blocks, and it will have different orders in these blocks. And so you do not expect, if you do a construction like that, to get an operator that's good on the properties. You have to take into account that they have different degrees. So you would need someone in the products to account for that. But part of the story is true. It's still a Rockland complex in a graded sense. That part of the analysis was quite.
How explicitly can you compute anything? Like if I give you the contact free sphere, like how far
Yeah, somebody computed that explicitly to modify the complex, the Romain complex a little bit to be able to compute that. Is from the torsion point of view not so interesting because there's only the trivial representation. And the last thing about the torsions is a function in terms of the representation.
Okay, the three doors.
I was about to present the result by Romain and Sechadri in the paper. They computed it for CR Seifert manifolds. These are contact manifolds, but as one action, locally free as one action that preserves the contact structure and the supplementary matrix. But might have orbifold singularities, and they were able to compute distortion and see that it is actually the in this case, this is still very special case with now symmetry. In general, it's not what we get.
But it's a Ray-Singer torsion of the three-point.
Yes, you do not.
So it doesn't
see the contact structure. And one of the big questions is, do you perhaps for other three-dimensional contact manifolds, does this torsion really coincide with the Ray-Singer torsion, or does it see the contact feet? It's not clear to me. That's an example where we would see that. Okay, so my plan was to show you actually an example where computed by hand. Not torus, but it's a min manifold. So we take the Heisenberg group, which is very simple example of a contact manifold. So we take the Heisenberg algebra, the three-dimensional Heisenberg algebra, you take the simply connected redo to that, and you model out the lattice gamma. So when you write G for the group, so the Lie algebra is G, so it should be three-dimensional. Generators x2, x2, x1, x2, x3, and x3 is the x2. But Heisenberg algebra for lattice, we take the lattice that's generated by x1, x2, that generates a lattice in the group, and you can model it out and you get a super-nil manifold on which the Heisenberg group still acts from the left, and we take a right invariant contact structure that's spanned by x1 and x2. We take a right invariant sub-Riemannian metric. We want a flat vector bubble to twist with, and for this we take a representation of the lattice the simplicity we can get. One-dimensional unitary representation that will be specified by two numbers. We have to say how rho reacts to one generator shall be divided into pi I. A is some real number, and rho of the other generator of the lens equal pi I. 2 pi I B, A and B two real numbers that specifies the representation here. We take not both 0 that will guarantee a simplicity. And we can actually compute distortion by hand in this case. The point is we can look at the sections of the flat bundle that's associated to this representation. And that can be decomposed. That is a module, this is a representation of this group G. The group G acts on the mid manifold, but it also acts on the sections of this bundle, So you can decompose that into irreducible representations of this nilpotent Lie group. And all irreducible unitary representations of nilpotent Lie groups are known by this construction of Kirillov. And in this case, it's particularly simple. This decomposes as a sum of some one-dimensional representations. The one-dimensional representations are assigned to two numbers. In this case, we have beta and beta O in the right pictures. These are two one-dimensional representations of the Heisenberg group, essentially those that factor through the center. And then more representations on M2 of R. Schrödinger representations, they come with the parameter H. And we have to take the sum over all integral H, which are non-zero. We get this Schrödinger representations, and they come with multiplicity. This comes with multiplicity, the absolute value of H. So you can very explicitly decompose the sections of this bundle into irreducible representations of the group G. And then you can look at the operator of each of these representations and work out the contribution to the zeta function in each representation. So there are two types of representations, the scalar representations. That's what I know that here I see alpha beta. When you do real numbers alpha and beta, we have a scalar representation. This scalar representation, the vector field x1.
Maybe Stefan, to make sure I understand. So this decomposition is basically like Fourier for the G, right? And the first one is like a typical Fourier, kind of in the direction of x1, x2, roughly speaking.
This is what comes from, you can model the S1 actually in the matrix. This is, of course, it comes from the base.
Okay, sure.
Is covered by these.
So
these are functions which are invariant under the circle action.
And how should one think of the other ones?
You can write down explicit formulas how they sit in these functions.
Okay. But they also look like oscillatory of some kind, or like, how do you think about
these
that?
are then functions on the total space of G, which have some equivariance properties with respect to gamma.
Yeah.
So these are the representations, and then you make that gamma invariant to produce sections.
No, but I mean, like the first ones, I mean, I see as the typical oscillatory exponential, right? Like the typical eigenfunctions that you would see in Fourier, right? But the other ones, what should I imagine they are?
Okay, maybe probably you're asking about this Kirillov.
Yeah.
You have to each coadjuvant orbit in this group, you associate one of these representations. So you pick a coadjuvant orbit and you choose a polarization, which is sub-modular. On this sub-modular, you pick a
Okay, maybe we'll less later. Okay, it's fine.
But then eventually you will have very explicit expressions for the representations. Okay. So this way you get representations of G, and then if you want function sections of this bundle, you have to force them to become gamma equivariant. Sure. And there are several ways of forcing them to become gamma equivariant, and we should use systematic. Okay. Okay, so in the scalar representation, it acts by the x1 acts by 2 pi I of x2 acts by 2 pi I beta, and x3 doesn't act at all, the commutator. This is what this scalar representation does. So you can look at the operator, say d naught star d naught in this representation, and it's 2 pi alpha squared plus beta squared. That's it's just a scalar, so you computed the spectrum, and the other operator. By the way, this has the same as the operator D2 star, and the different ones. It's the one in the middle, and here you can compute the spectrum 2, and the spectrum you get is 2 squared alpha squared plus beta squared. Well, this is just a 2 × 2 matrix. You have to compute the eigenvalues of this 2 × 2 matrix. It has a 0 eigenvalue, and this is the other eigenvalue you get. And notice that this is just a square, the square of this one. So if you look at the zeta function in this representation, so if you look at the graded trace in and you look at this operator, but just in this representation, because it's 0, it's 0 all the time. The whole zeta function of this combination of zeta functions, if we combine it, the Laplacians vanishes in this representation. And then there's a second type of representations, which we will representations and more exciting. So we will represent this. There are L2 of R, and we define a parameter H, a real parameter. And here the action of x1 is just okay. What the mention is married to d by dx, and it's 2 x by the sigma of H. Some factor 3 pi H times x, and x3 x by the commutator, which is 2 pi. You see the parameter. Parameter tells you how the center is. So these are the Schrödinger representations, and Kirillow's construction tells you that these are all the irreducible unitary representations of the Heisenberg group. And if you look at the operator E naught star naught in this representation, what you get is 2 pi times H, and then you get minus d by dx squared plus you get a harmonic oscillator in this representation. Oscillator. And particularly, you know, the spectrum explicitly. Spectrum. The spectrum is 2 pi H 1 plus. So this operator is the sub-Laplacian, and the representation becomes a harmonic oscillator. You know the spectrum explicitly. The operator D2 is the same. It has the same spectrum. And then you can also look at the D1 star. D1 spectrum. slightly more complicated, but you can work out what the spectrum is, and it turns out to be precisely the square of that we have here. Explicitly too. This is a matrix of operators, 2 + 2 matrix of operators. Yeah, you work at the spectrum explicitly, and again, you see that because this is just the square of that, the theta function we get from this representation. If you look at this, it's not opposite. This representation is constant in 0. So every irreducible representation gives you 0 contribution to this theta function. And then, of course, if you have the decomposition I wrote down here, the theta function on the middle manifold, so that we can trace on the middle manifold is functions here. And of course, there's the torsion is trivial. The torsion is trivial. The contact torsion in this case is trivial, and it's the same as the symmetry, which is trivial to in this case positive. So here, like, so we can still by hand using non-commutative transform to spectrum and we don't get anything inside. Admit. You could do a little more. I mean, since you have like explicit formulas for the spectra, each individual operator, you could like actually compute the determinant of the sub-Topology in this case. And you have just have to this the function associated to them as a rule. We would see the function again, and we could work out the derivative here. But in the torsion, these operators are being combined in a way that is expensive. So here's one example where this contact actually computes the Racine torsion. And there are theorems. Little is known in general, but we have this theorem I mentioned before. They prove that this contact torsion coincides with the Racine torsion. Yeah. For certain representations, for unitary representations of the fundamental and only over certain 3-dimensional manifolds. For CR cycle. So a CR cycle A, this is a smooth 3-dimensional manifold A that has a decimal free circle action. And this circle action preserves the contact structure. Circle action is actually is generated by the read vector field of the contact form that's being preserved. And the sub-Riemannian metric too is invariant under the circle action. The circle action need not to be free, so the quotient n by the circle action might be modified. But for these kind of manifolds, they can show, for these kind of representations, they can show that their torsion coincides with these. There's one result that's available. Another result, even more recent, is the argument now. 2022. They can show that this comparison between the contact torsion and the Racine torsion is given by local quantities. It's an integral over some local quantities. And the local quantities, and that depends on the Riemannian metric it enters and the fiberglass emission metric it enters. And well, the contact quantity, but this can be computed locally. For general contact angles, this is available. So the big questions here are, of course, what is this local quantity? When you compute that, in a simpler question that arises is if you look at this contact torsion, you can vary the sub-Riemannian metric and ask how does the contact torsion change if I vary the sub-Riemannian metric. This is given by local quantities again, and of course just compute these local quantities. Little is known here. And maybe another question that might be interesting is not to look at the derivatives and this the function at 0, but look at its value at 0. It's something that should be easier to compute. This is given by the constant term, the heat kernel expansion here. And yeah, for three-dimensional contact manifolds, it's known that it vanishes, and that's good. That's what you would hope for, probably. For the higher dimensional contact manifolds, it's not clear if this is zero. That's true. If you rescale your sub-Riemannian metric by constant, the torsion will change in a very critical way, and it will change exactly by this quantity. So if this vanishes, that means rescaling your sub-Riemannian metric by constant does not change the torsion. You might want to rescale with the function, that would be more involved, of course, but this is sort of like the most basic conformal invariance you could ask for, is to ask this to be 0. That's just whether it's the case or not. For three-dimensional contact manifolds, could be 0, and in general, we don't. What you do know is that this is a contact invariant. This quantity here does not depend on the metric. Shows that this quantity does not depend on the fiberglass emission metric, and it remains unchanged if you move the contact structure. It's within the classic contact structure. But that's not a statement due to very stability. But it's a contact invariant here. The non-zero unit. In this theory, torsion is nicely under control. Okay, so this is how much I intended to say about contact manifolds.
Stefan, can I ask
Yeah,
you?
sure.
What happens? Have people use also this Witten deformation bismuth approach in this case?
Not to my knowledge. This Witten approach compares the analytic approach to a combinatorial dynamical approach using Witten-Morse function. What people do with the contact torsions, they compare it with the Racine torsion, the other analytic approach. And there's a very natural comparison. You can do sub-Riemannian limit, you can sub-Riemannian metric, and rescale it with different speeds in the contact direction and the transversal direction. And you would expect that in the limits that the contact torsion will appear. And that's exactly what argument for are doing. Considering this sub-Riemannian limit and the work that is the expansion and observe this show the result. Okay, so how much my time?
15.
Okay. Okay, then let's turn to the last part of the talk. This is about particular five-dimensional manifolds. Which carry 2, 3, 5 geometries. So what is that? That's specified by a sub-bundle of rank 2 in the Phantom bundle. that is as non-integrable as possible. So if you take sections of H and look at the bracket, any bracket is not going to be contained in H, just like in the compact case. And the most you could hope for is that if you look at the boundary E, that you get the spanned by three brackets of sections of A, this final rank 3. And then if you take triple brackets, so you take brackets sections of H and sections of E, they span up, you assume that they span all of the antibalance, so you assume that the line is 5. That explains the numbers 2, 3, 5. The filtration you get on M. Filtration now. This is the rank 2 subbundle, this is the rank 3 subbundle, and this is all the tangent bundles. So this is numbers 2 to 5. So the bundles spanned by the brackets go as quickly as they possibly do. Okay, so this is one particular kind of frequent geometry. But note that this is a generic condition, this is C2 open condition. If you compare H a little bit, but with respect to the C2 topology, this is probably one change. There's an open condition. And just like in the contact case, you associate, you look at the associated gradient bundle, it's just H plus E over H plus T over E. This is what one calls the associated gradient to this filter. And the bracket of the Lie bracket of vector fields induces an algebraic bracket. So this becomes a bundle of gradient equivalent 3 algebras. Just as before, now slightly more higher depth. The point here is that the Lie algebra we get in each fiber. By the way, these Lie algebras are called single algebras or osculating algebras or nilpotentizations. So many names for these algebras you get here. This is a Lie algebra. It's a graded Lie algebra. It composes into 3 parts, and the Lie bracket is compatible with the grading. And it's always the same Lie algebra. In each fiber we have the same Lie algebra. The bracket we have base, graded base x1 to x5, and the brackets, the non-trivial brackets are x1, x2 is x3, just like in the compact case. But then x1, x3, x4, and x2, x3. Okay, so these are some filtered manifolds. So like here about these. Let me give you a few examples. We can take the neighborhood, we can take the Lie group that corresponds to this Lie algebra and take the right invariant structure, and we get a manifold to start. We can look at nil manifolds, we can draw out the lens with those examples. More interesting are rolling surfaces. It's a mechanical system. Class of examples from mechanics. You start with 2 Riemann surfaces, and then you let one roll on the other one. You get a configuration space that's 5-dimensional. Configuration is like a point in one surface, a point in the other surface, and then isometry between the tangent spaces, how they sit on top of each other. And then you let them roll. You want them to roll without slipping and without twisting. And this condition, no slipping and no twisting, can be encoded in the rank 2 plane bundle in this configuration space. And generically, it turns out that this rank 2 plane bundle is a 2-3-5 geometry of this type. More precisely, it is a 2-3-5 geometry of this type if and only if the Gaussian curvatures of these 2 surfaces of this geometry. Gaussian curvature at any point in the one surface is different from the Gaussian curvature at any other point in the other surface. Even only if this is the case, it is going to be of type 2, 3, 1. And something quite interesting happens here. If you take a round sphere and roll it on another round sphere, and you make the radius of the one sphere just 3 times as large as the radius of the other sphere, then you get a configuration space that is functionally S2 cross S3. But it turns out that all of a sudden you get way more symmetry than you would expect. And this turns out to be a homogeneous space of the exceptional weak G2. And you log out the particular parabolic subgroup G2. So this is 14-dimensional symmetry all of a sudden. So these are some examples. One of the basic questions I'm interested in is what sub-manifold, what 5-dimensional manifolds that meet such a structure. And it's an open condition, but if you work with those manifolds, it's not at all clear which it needs such a structure. The interesting thing, it's probably hinted on by this example here already, geometries, 2, 3, 5 geometries. A one-to-one correspondence with regular, normal, parabolic geometries. That means, in some sense, in the sense of parabolic geometries, they can be described as curved analogues of this homogeneous space of this generalized flag directly. This is an observation by Catal. It's a theorem by Catal. It's not at all obvious. This is the same thing. But you see these geometries like closely related to the exceptional equal G2. This is the real form of G2 that appears here. That has several consequences. See the Catal geometry, parabolic geometry, curvature tensor. So these geometries have a curvature. It's called harmonic curvature. This is a section of the fourth symmetric power of H star. So without choosing any metrics or any additional structure, just having a 2, 3, 5 structure, you can cook up harmonically, though it's rather complicated to get explicit formulas. Curvature tensor in this power. And is a complete obstruction to local factors. And the power start to this harmonic curvature manifest even only if the 2, 3, 5 geometry locally is homomorphic to the omnipotent V, which is equivalent to saying locally differomorphic to this vector variety. That also tells you that the group of diffeomorphisms, or that the group of automorphisms of the 2, 3, 5 structure is always a finite dimensional V group, and the dimension can be at most as large as the dimension of G2. This is the most symmetry you possibly have is 14. So finite dimensional automorphism groups. So this tells you in particular there's a curvature tensor, so we do not have custom theory. So like in complex geometry, that they all look a little bit alike. They have a curvature is different, and they don't even look alike. So I have to speed up to do that. So there's some interesting topology. If you have a 2, 3, 5 manifold, then the tangent in an orientable case, the tangent bundle will be isomorphic to this associated gradient, of course. And in the orientable case, the one-dimensional, the rank, the line bundle we have is just trivial, and you can use it to identify the third component with the first one. So the tangent bundle has to be rather simple. It has to decompose into a sum of two copies of a line bundle that's orientable, complex line bundle that's orientable, and a true real bundle. That is a strong condition on the manifold. That tells you that the manifold is spinable. It also tells you that the Pointryagin class of M is related to the Euler class of this sub-bundle H. There's some relation between. You have to have the fractional Pointryagin class. And it has to be the square of the Euler class. So not all H can appear. And if the manifold is closed, then the Kerbier semi-characteristic has to vanish. This is a what-2 invariant. Just add the ranks, add the dimension of the vector numbers, mod 2. It's the Kerbier semi-characteristics. And if your manifold has a orientable subplane bundle of rank 2, then the Kerbier semi-characteristic has to vanish by a theorem about here. So there are some strong topological restrictions for a closed manifold to admit such a structure, just from a topological point of view. You can ask if this is sufficient. Suppose all these conditions here are met. Can I decompose my tangent bundle like that? The answer is yes. So that's worked it out in collaboration with Chantal and Barber. We can show that the Kerbier semi-characteristic vanishes, and this situation was in connection between both the tangent bundle like that. But that does not tell you yet that you actually have a 2, 3, 5 structure. If there was an H principle available, then you could apply that and conclude that there's a 2, 3, 5 structure, but it's unknown if there's an H principle for those manifolds. I think Alvaro knows how to prove this H principle, so if he succeeds. So there's some interesting topology here. And then in the last minute, what I'm currently working on is we look at the Romain complex for these geometries. It just looks like the contact case. There's a complex of differential operators that's intrinsic to this 2, 3, 5 geometry. Now the operators have higher orders. There are operators of order 1, 2, and 3 that appear in this complex. But you can use formal edge lines and proceed exactly the same way in the contact case and define an analytic torsion for these manifolds. And there are all kinds of questions. All the questions that were left open in the contact case are open in this situation too. It's even harder to compute this local invariance. The only computation I could do was for nil manifolds, five-dimensional nil manifolds. What I could show is that the Riemannian torsion and this analytic torsion associated to the 2, 3, 5 geometry, well, they differ by a local constant, something that's constant in the representation. So the space of representations you have there is like disjoint union of tori, and this torsion is essentially a function of this disjoint union of tori. But if you compare it with the Riemannian torsion, then you get a portion that's a function of this disjoint union of tori, which show that it's actually constant on each connected component, but not constant in general. So it feels like it could possibly, this very simple example, coincide with the Riemannian torsion. And I wonder if it can be for what general 2, 3, 5 geometries, it does see anything of this geometry. I mean, the simplest situation would be that we eventually be able to prove a theorem that tells you how this torsion is justified. After going through all the trouble, it just computes what the Riemannian torsion computes. Perhaps, I don't know, this torsion sees more and can be used to distinguish geometries of this type. Maybe provide obstructions, additional obstructions to the existence of the closed manifold. Maybe tell them apart, say if they are homotopic. This invariance must coincide. Actually, yeah. So one thing you can prove is you can like start there in geometric and look how does this torsion change, and this computation goes through just like in the Racine paper from the 70s, essentially with the Heisenberg calculus. You can show that the variation of the torsion will be by local properties. Moreover, you can ask now what happens if I start deforming my 235 structure. It's an open condition, so if I deform it a little bit, I stay in this class of 235 structures. But now there's no double theorem, no gray stability. So that is might look totally, even a small perturbation might produce a 235 structure that doesn't even locally look like the original one. So it is an actual question whether what the torsion does under a perturbation like that. And there you too can show that the torsion will only vary by local quantities. But actually working out these local quantities is so far not possible. Yeah, okay, let me add one more comment. Why these weird geometries, contact and these 235, the Riemann complex is available for all manifolds. But the analysis, the Riemann complex is suggested in the definition of the analytic torsion only works if the single algebra has a particular property. The single algebra needs to have pure cohomology. Just you need a graded input and D group G with pure cohomology. There's a graded input and D group, there's a grading automorphism. That grading automorphism gives you an action cohomology. So on the pure cohomology of the D algebra, you have the grading automorphism that acts here. And what you need for this analysis to make sense, you want this to act as a scalar in this cohomology. Then the formal adjoints work out, then you can do all the analysis. And so I'm curious if there are graded input and D groups with which have pure cohomology. And I only know 3 examples. And one example is the abelian D algebra that gives the Racine torsion. Then there's the Heisenberg algebra that gives the contact torsion. And then there's this 235 algebra that appears here that gives you the torsion as sketched very briefly here. And I do not know of any other graded input and D group that has this property. So I do not know of any other field of manifold where I can find an torsion just like that. And I find that very curious. So you can turn on the computer and rule out all kinds of graded input and D algebras, which feels like a number theoretic problem behind that. And I find that very curious. It's only these 3 apparently are right. Okay, sorry for using that.
Hello. Questions?